Hello everyone and welcome to lecture. Today's lecture will be about optimization and specifically solving for the maximum and minimum value of a given function in an optimization problem. So specifically what we'll start with is talking about optimization in 1D for scalar valued functions. And what you'll hopefully recall is that the main theorem that we have for optimization in 1D is that the absolute max and min sometimes called the global max or min of a given function occurs at one of two locations. And this is specifically at either A, an interior critical point of the function, interior to the domain under consideration, or B, on the boundary. Of the domain. And a picture illustrating this is the following. Suppose we have a function of x. So we have some function of x, and we have an interval from a to b, and the function of x starts here at a, at this point right here, and then maybe looks like this, up until b, where it hits this value, and then it's right where we're considering maximizing and minimizing the function on this interval from a to b. You'll notice that the function that we've drawn has a number of different critical points. One here at x1, at x2, at x3, x4, and then lastly at x5. x3 is a critical point of type 2, where the derivative does not exist. And the other critical points, x1, x2, x4, and x5, are all critical points of type 1. Where the derivative at the point is equal to 0. Or the instantaneous rate of change at the point is equal to 0. And you see very clearly from this example function that all of the critical points are local maxes and or mins of the function, but the global max and min only occur at two separate points. The global minimum of the function occurs here at this critical point at x3. So we say that x3 is an absolute max, or absolute min of the function on the interval from a to b. And the absolute maximum of the function doesn't occur at any of the interior critical points, but it occurs on the boundary. So it occurs at the boundary point of A. So this is a nice example function showing exactly where the maximum and minimum, the absolute max or global max and min of a function can occur. So it illustrates this theorem for us. So it turns out that for multivariable functions, we have this exact same theorem, almost word for word. And we'll visualize that for functions of two variables, but this theorem actually applies for functions of any number of variables as well, which is why we can actually state and solve optimization problems in any number of dimensions for any number of functions. Definitely becomes more complicated for higher dimensions. But we'll look at what this says for 2D right now. And I guess we'll state the theorem in general. And the theorem says the following. The absolute maximum or minimum value of a function of n variables on a closed bounded region and we'll call this region omega in n-dimensional space occur at either one of two locations. The first possible location is at an interior critical point. Inside the region omega. So remember, this is a point of two possible types. The first type is where the gradient of the function at a point is equal to the 0 vector, or all of the partial derivatives are equal to 0. Or a point of type 2, where one of the partial derivatives at the point does not exist. You'll remember this is our second type of critical point. So the absolute max or min of a function occurs either at an interior critical point or at a point on the boundary of this region. So a boundary point of the region omega. So this is our main theorem for optimizing functions of more than one variable. In 2D, we know we have multiple different ways of visualizing this this statement. I think a nice way of visualizing it in 2D is to look at the level curves of a function, and specifically, if you have some domain that you're interested in optimizing over, it could be very complicated. Maybe it looks like this, and then this is the region D that we're optimizing over. And then maybe the level curves of the function look like this. So with the function shown here, you have a possible min or max right here, a possible max right here, possible max or min other points on the boundary, but all within the set D. You have multiple different points on the boundary, which could be max or mins, and you also have that there are a number of different interior points, which could be maximums or minimums of your function. So a lot of times, just looking at the level curve plot or a density plot in 2D of the function will give you a good idea of where the max or min is. But you see that this is consistent with that theorem. It's saying that at the interior critical points of this function, of which there are, for the drawn example, there are 2 interior critical points. The global max or min of the function could be either at these interior critical points or on the boundary, as the only 2 possibilities for maximizing the function. Another nice graphical interpretation of this, as we've seen, is for a function of 2 variables, we can plot the graph of the function, so the surface plot of the function. If we make a third axis and we visualize this third axis, then what this looks like is you'll have an x-axis, a y-axis, and a z-axis, and some domain down here in the xy plane that you're optimizing over. And then the function itself, if you plot the surface plot, z equals the function of x and y, you could have, say, a global maximum right here maybe. Maybe the minimum of the function occurs at an interior critical point right here, where the function kind of goes down and then it dips down maybe to this minimum. And the global maximum maybe occurs here on the boundary. And then for all other points, maybe the surface looks kind of like this. So for example, this could be a surface plot of a given function of multiple variables, but you see that you have maybe that the global minimum of the function occurs at an interior critical point, where this is the lowest possible value of the function, and then the function just sort of, the surface of the function maybe hits a maximum right here, at this point right here, where this is a boundary point on the domain that you're considering. The idea and the hopeful generalization that you can see is that this applies in general, right, for any number of variables. So even in 3D, say, if you're considering, say, like the level surfaces of a function, where you have a function of 3 variables, say, so in both these examples, we have some domain D that we're optimizing over, and very often in 2D, we'll use the notation D for a domain. But this also applies in 3D as well. So say, for instance, you have some region, some 3-dimensional region, omega. This is a 3-dimensional surface. And you have possibly a temperature function or some other function of 3 variables that's defined on this surface omega. This theorem still holds, and it still says that you can find the absolute max and mins of your given function on this 3-dimensional region at either an interior critical point of omega, to the domain omega, or lying on the boundary of omega, which is going to be, in general, some type of surface. So this is our main theorem that we can use. We're going to see that there are 2 main problems that we have to consider in any number of dimensions when optimizing a multivariable function. And the big issue here is that the maximum and minimum values of a function severely depend on the domain on which we're optimizing over, which are typically problem dependent. And this is the same problem that you face in 1D as well. The global or absolute max and mins that you solve for in 1D are heavily dependent on the domain at which you're optimizing over. So let's say we have some function of 2 variables with 4 critical points. If you were to say pose an optimization problem on this domain, call it D1 here, in general, the solution on this domain D1 is going to be distinctly different than the solution to an optimization problem on this domain D2. You can label the critical points, say like P1, P2, P3, and P4, and you can see clearly why. For both of the functions, or for both of the domains, you're dealing with the same function of 2 variables, but the optimization problem on D1 gives us that the 2 interior critical points to the region D1 are P1 and P2, and you potentially have a whole bunch of other spots on the boundary where there are maximums and minimums on the domain D1. For the domain D2, D2 definitely shares the critical point P2 with the domain D1, but it also, inside this domain D2, you have a new critical point, which is this P4 right here, and you also have a different boundary. So you have a whole bunch of other potential locations for a max and min of the function on the boundary. For both domains, P3 is outside of the interior of both of the domains. So this is not, P3 is not a possible max or min for either of these 2 domains, D1 or D2, because P3 is a critical point that's outside of both of the domains. But you have this exact same issue in 3D as well. If you were to say draw out a function of 3 variables and look at the potential max and min locations for 2 separate domains in 3D, you'll see that this exact same problem or potential problem pops up. Let's say again you have a function with four separate critical points, all located at different locations in 3 dimensions. And then you pose an optimization problem over some 3-dimensional domain. We'll call it omega 1. Where these critical points all lie inside of this region, omega 1. And then let's say you have a similar scenario where you have some other domain, omega 2, that only contains 2 of these critical points of our function of 3 variables. And you can also label these critical points very similar to the previous problem for a function of 3 variables. You still have the same issue where if you're doing an optimization problem on omega 1, the solution in general to that optimization problem will be either at those 3 interior critical points that are inside omega 1 or on the boundary. And same thing for omega 2. But for omega 2, you only have 2 interior critical points, P2 and P4, or on the boundary of that new domain omega 2. So this is definitely one potential issue that is very important. You always have to consider whether or not your critical points lie inside the valid domain that you're looking for to solve the optimization problem. The second issue, and an issue that is also very important to talk about, is specifically, you can see this in domain 1 here in this first example, is that you could have a piecewise defined domain. So here D1 is what's called a piecewise smooth domain, or a domain that can only be described with piecewise functions. So by breaking it into separate parts and dealing with each piece individually. In which case, this theorem still holds and it's perfectly fine, but you have to be careful to analyze every separate piece of the domain when you're looking for a potential max or min on the boundary. And this also holds in 3D as well. Most domains that are describable, in order to describe them nicely, you have to break them up into multiple different pieces. So a perfect example of that is a rectangular domain in which you have multiple different pieces that describe a rectangle. So if in 3D, say, you're trying to optimize a function over a rectangle, well, you're going to have to break that rectangle up into the 6 faces of the rectangle, all the multiple different faces, and consider separate optimization problems on each individual face. That's for a 3D optimization problem. Similarly, in 2D, if you're trying to find the maximum of a function over a rectangular domain in 2D, you're going to have to break that up into the rectangle, each one of the separate lines, the boundary lines or boundary curves of the rectangle. So in order to check the boundary for this example, specifically if we have this shaped domain, we'd have to break the boundary up and consider separately each one of these separate pieces to this domain right here. But what's nice is that this theorem still holds. So you'll see that the easiest optimization problems to solve on the boundary are problems with a nice smooth boundary that can be parameterized. And typically what we do for the first approach towards optimizing on a boundary is find the parametric curve representation for that boundary. So we use parameterization and parameterization of curves from a previous calculus course. Now, by the end of this section, we'll also talk about a separate method to deal with constraints like this, which is called Lagrange multipliers. But this will be for the topic of the next lecture. So specifically here, we'll just use the example of the function x times y times e to the negative x squared minus y squared. Because we know that we've already went through and solved for the critical points and classified the critical points of this function. This function has 5 critical points. One saddle point at 0, 0, 2 local max at negative L, and L, comma L, where L here is 1 over the square root of 2. So I'm going to use this simplification to avoid writing 1 over the square root of 2 multiple times. And there are 2 local min. One at negative L, comma L, and one at L, negative L. And this was, done in the last lecture. And so the idea here is that if we now consider an optimization problem over a number of different regions, the solutions to this optimization problem are going to be different, right? Very, very strongly different depending on what regions we choose. For instance, if we pose an optimization problem finding the global max and min over some domain D1, where D1 is the set of all points x, comma y, such that x minus L squared plus y minus L squared is less than or equal to 1. Right, this is an optimization problem over the circle of radius 1 centered at the point L, comma L. If we open up Python to get a visualization of this, we're going to see very clearly that the maxes and mins are going to be in different places. So here we see a contour plot, right, of the full plot of this function on a rectangle from negative 2 to 2 in x and y. But we've kind of restricted to just this circle right here that we're interested in for this domain D1, this region D1. So the surface plot is only going to be showing this this region, surface on the region that we're interested in. And we very clearly see, right, when we look at this, that the results of our theorem are directly holding, that the global max and min on this region, with respect to this region, is occurring at either a maximum point right here, or at a local maximum, which is a critical point in the interior of the domain, or it's occurring on the boundary. The global min of this function is occurring right here on the boundary. You can very clearly see that. There's also the saddle point, right, which can neither be in the absolute max or the absolute min, because there's always points around it that are higher and lower than the point itself. But this is a very, very nice picture. But the point here is that if we change this region, the optimization problem changes and the solution is going to change, just like in 1D for 1D functions. For instance, if we consider domain, we'll call it D2, we do the optimization problem on D2. This is all points x, y, say, such that x minus 1/2 squared plus y over 1/2 squared is less than or equal to 1. This is in ellipse that's centered at the point x equals 1/2, y equals 0, with a semi-major axis of 1, or a equals 1 along x, and a semi-minor axis of 1/2 along y. So the b of the ellipse is 1/2. So if we look at a Python plot of what this is giving us, right, this directly corresponds to this region right here. And going to have much different solutions than the previous optimization problem. Specifically, there are no critical points except for the saddle point right here inside this region. So the global max and the global min are going to occur on the boundary of this region. That's very clearly being seen, right, if you look at the boundary curve of the graph, or on the graph of this function. Global min occurs right here, looks like. The global max occurs right here, and you can very clearly see the result of the theorem, and you see that the solution is in general different than the previous case. And I want to go over one more possible domain, and this is a piecewise domain, because in general you can consider not just smooth domains like these ellipses that I've shown, but you could also consider, say, a triangle, or in general, a rectangle, which is our standard plotting domain. So to illustrate this, we'll just kind of look at this function on one last final domain, say D3, which is, we'll say, the set of all points x and y, such that x is greater than -2, or greater than or equal to x. X is greater than or equal to -2, and y is less than or equal to +2, and y is greater than or equal to x plus 1. This is a triangle in the xy plane. Okay, and again, our theorem is still going to hold. Specifically, if we open up our Python plot here, this is exactly what we see right here. So we have, this is x equals -2 right here. This is the line y equals x plus 1, and this is y equals this is x equals -2, y equals +2 right here. So this gives us this triangle, and if we were to say go to solve our optimization problem here, we're going to have actually that the global minimum now occurs at an interior critical point, and the global maximum in this region occurs on the boundary. And we can very clearly see that when we kind of rotate this a little bit and look at the graph of this function, where you see that on the boundary, you kind of have it goes down and up, and then right here is where the global maximum is hit, at this point right here on the boundary, and then it goes down to this minimum value right here, but the true global minimum in the region occurs at an interior critical point. So I think these three pictures that I've shown, these three separate domains, really clearly illustrate the point, and it also kind of illustrates what we're going to do on the boundary, right? Even if we have a piecewise boundary, what we do is we break it up into all of the different pieces, and then for a function of two variables, we can use single variable calculus to calculate the local max and min on the boundaries themselves. And then you just compare all of the values. So we'll see that in our examples a little bit later on.